Statistics is the science of data. So let's imagine we have data. We have the weights of 500 cancer patients. We have the productivities of 600 wheat fields. We've got the mileages on 700 cars. How do I deal with that? How do I take that, all that data, all those numbers, and how do I boil it down? How do I summarize that? How do I turn that into something I can understand in just a very short amount of thing without reading every single number on my list? What we want to do is compute summary statistics. So the first thing I want to do is, if I've got a big long list of numbers and some are big and some are small, the first thing I want to do is try to get a sense of where's the middle of this list. Where's the center of that? The mean, the median, and the mode are all numbers which tell us, in slightly different ways, something about where the center of a list of numbers is. So, the mean, the average, hopefully we all know about that. We know how to compute an average. So, let's see, here's a scenario. Suppose I go out and I survey 5 people. I say, how many pets do you have? The first person says, I have 1 dog. The second person says, pets. The third person says, I have 2 goldfish. The fourth person says, I have 3 cats. The fifth person says, I have 1 dog. So my numbers are 1, 0, 2, 3, and 1. If I want to compute the average, the mean of that, I add them all up and divide by 5. 1 plus 0 plus 2 plus 3 plus 1 is 7. 7 divided by 5 is 1.4. Therefore, I can conclude that in this sample, among these 5 people, we have an average of 1.4 pets. R, of course, is wonderfully adept at computing all these sorts of things. First thing I would do is I would create my variable, pets, and then I would say, let's create a list of numbers, 1, 0, 2, 3, 1, and then I apply the command mean to that, and it will quickly and easily compute that the average of this list is 1.4. All right, what's the next thing I can do? The mode. The mode is the most common number on the list. That's the most frequently occurring number. Now, in this case, I have 2 people on from my sample who had 1 pet. So as a result, the mode would be 1 pet. If all the numbers are different, then there would be no mode. The median is the middle of a list. If I took all the numbers on that list and I ordered them from smallest to biggest, so the first thing I do is I take my 1, 0, 2, 3, and 1, and I put them in order. So now they're 0, 1, 1, 2, and 3, and then I take the middle number on the list, which in this case is 1, and that's the median. If there were, in this case, I have a clear median because there's an odd number of numbers on the list. I have 5 numbers. If there were an even number of numbers, then you take the middle 2 and you average those. So R, of course, is very, very good at this. I would simply type median of my data set there, pets, and it would compute that the median of this list is 1 pet. Quartiles are another way of describing this. Okay, so I want to get beyond just measures of center. I want to talk about how these numbers are distributed now, more than just the middle, the mean, the median, and the mode. Now let's talk about quartiles. A quartile is the first quartile on a list is a number that would have a quarter of the numbers below it and 3/4 of the numbers above it. So, okay, again, I put the numbers in order, just like I would when I'm finding the median, and then I pick out that number that has a quarter of the numbers below it, 3/4 above it. In this case, the number 1. That first one has 1 number, 1 of the 4 remaining numbers below it, so zeros below it, 1, 2, and 3 are above it, and so therefore the first quartile is 1. The third quartile, on the other hand, has 3/4 of the numbers below it and 1/4 of the numbers above it. So that's 2. 2 has 1 number above it, that's the 3, and it has the other 3 numbers, 0, 1, and 1 below it, and so that's what quartiles are. The second quartile, well, that would be the median. The second quartile would have half the numbers above it, half the numbers below it, and we already know what a median is. So percentiles now are a generalization of this idea. So again, it's picking out numbers that have certain percentages of the remaining numbers above or below that. The 10th percentile, for instance, would be a number that has 10% of the numbers below it and 90% of the numbers above it. The 60th percentile would have 60% of the remaining numbers below it, 40% of the numbers above it. So in that sense, the first quartile is also the same thing as the 25th percentile. The median is the 50th percentile, and the third quartile is the 75th percentile because it has 75% of the numbers below it, 25% above it, and that's percentiles. All right, so we've got something about the center. We got these quartiles, we got these percentiles. The next thing I want to do is start to describe how spread out the numbers are. If you tell me the average of a list, that's great to know the average, but then it's like, well, are most of the numbers close to average? Are most of the numbers far from average? Are these numbers widely scattered, or are they all bunched up right in the middle? So one of the simplest things we can do is we've got our quartiles, and we can calculate the interquartile range. Take whatever the third quartile is, subtract the first quartile from it, and then that tells us something about kind of how spread out it is, that interquartile range. Well, since it's between the 25th percentile and the 75th percentile, it has probably 50% of the numbers between those two. So in this case, my third quartile was 2, my first quartile was 1, 2 minus 1 is 1, and the interquartile range is 1. Even more useful than that, more commonly used, we're going to use this a lot in this course, is the standard deviation. The standard deviation takes every single number in the entire list into account, just in the same way when you're taking an average. All the numbers are involved. The standard deviation involves all the numbers, but it's measuring kind of how far things are from average in a very, very rough sense, just to get a gut feeling about it. The standard deviation is kind of trying to compute something like how far the numbers are from average on average. Now there's some wrinkles and complexities because, well, we got some numbers above average and below average, and if I just average the differences from average, positives and negatives, so we square them and we divide by some stuff, and it's messy and complicated, but fortunately R knows all about computing standard deviations. If I want to do it in this case, I type SD, open parenthesis, pets, close parenthesis, and then it computes my standard deviation of my list. In this case, that's 1.14. That's the standard deviation of this list. If every single person in my survey had the standard, I don't know, everybody has exactly 2 pets, then the standard deviation would be 0. If all the numbers on the list were 2, 2, 2, 2, and 2, then my standard deviation would be 0, since all my numbers are exactly bang on precisely equal to the average. So this kind of tells me, in a very rough sense, how far from average are you on average. All right, now, so one thing we're going to be talking about a lot is the 5-number summary. Again, I got a long list of numbers. I've got 500 mileages on 500 cars, and I want to get a sense of what this set of numbers looks like without looking at every single one of them. It's really useful to get a 5-number summary. So what you do is you list the minimum, the smallest number on the list, the first quartile, the median, the third quartile, and then the maximum, the largest number on the list. R is, of course, designed to do glorious things like this. So I just type 5num, open parenthesis, pets, close parenthesis, and it will give me the 5-number summary telling me what these things are. So, all right, let's do an example on this. Suppose I have the weights of 3,500 heart patients. We then find the 5-number summary of this list. I'm not going to sit here and read all 3,500 weights. No, the 5-number summary is 95, 150, 185, 220, 310. So 310 is the maximum, 95 is the minimum, 185 is the median, 150 would be the first quartile, 220 would be the third quartile. So just suppose, I want to say, well, how many patients would weigh less than 150 pounds? I look at the list and I notice, 150 pounds is the first quartile. So that means that 25% of patients would weigh less than this and 75% would weigh more. So since I want to know how many weigh less than this, I compute 25% of my total number of patients, 3,500, and that is 875. So based on this, I could say, 875 patients would weigh less than 150 pounds because 150 pounds is the first quartile. So now I want to display this. All right, it's fun to look at numbers. I mean, hey, we all love looking at numbers all day long, but the human mind is far, far better at learning from graphs and diagrams and figures and plots and all those sorts of things. One of the most useful kind of plots we have is called a box plot, and it's a way of displaying a 5-number summary. So it goes from the minimum on the far lower side here. So here we've got, what are we looking? We're looking a box plot of daily average temperatures in Madison, Wisconsin for November 1940. All right, so it looks like the very minimum, the coldest temperature was down around, looks like about 13 degrees. The very maximum temperature in the month of November in 1940 looks to be, what's that, about 55 degrees. Okay, so there's the maximum and the minimum. And those are that we got these whiskers that go up to those. And then we got this box in the middle, which goes from the first quartile. We got a line drawn at the median and up to the third quartile. So the box goes from the first to the third quartile. Looks like the first quartile is about 23 degrees. So about a quarter of days were colder than 23. 3/4 of days were hotter than 23. The median appears to be, just about 35-ish degrees. So half of all days had a temperature below 35, half above 35. The third quartile looks to be 44. So 3/4 of all days were colder than 44. 1/4 of all days were warmer than 44. So just by looking at a box plot, I can get a pretty good sense of how the data is organized without having to read all the different numbers. Another really useful sort of graph that we're going to be doing all the time are histograms. Histogram shows you how many data points are in different ranges. So now it's basically a type of bar graph, and the height of the bar tells us how many things we've got in this different range. So like here we've got 6 bars. And if I look, let's see, the first bar goes from, we're studying the heights of black cherry trees. So we've got a whole bunch of them. And the heights of black cherry trees, apparently 3 trees had heights between 60 and 65 feet. 3 trees had heights between 65 and 70 feet, different 3 trees. Looks like between 70 and 75 feet, we had 8 trees in that height range. 10 trees had a height range between 70 and 80 feet. There were 5 trees that were between 80 and 85 feet tall. And then, holy cow, look at this, between 85 and 90 feet tall, there were 2 black cherry trees that were that tall. And so the histogram gives us a sense of the shape of the data. The height of the bars tell us how many things we have in each of these ranges. And then on the x-axis, the horizontal axis, we're describing what the ranges are. So there's our summary. Okay, we have learned measures of center, the mean, the median, and the mode. We learned something about percentiles and quartiles, measures of spread, or the interquartile range, and even more usefully, the standard deviation. And then from these, I can get a 5-number summary. I can display a 5-number summary with a box plot. And then a histogram, a bar graph where the heights of the bars tell me how many things I've got in these different ranges, is a great way to display my data.